Hello, good morning, good evening, good afternoon. Why is this view so weird? Hi, Jesus, how's it going?
Hi, Alex. How are you? Yeah, it's a bit different now. It looks more as
Yeah,
what we're used to.
yeah. This is
Good.
this, the other one was a little bit more zoomed in than I wanted it to be.
Good stuff. How are you? How are you, Alex?
I'm
Thanks.
good.
Thanks for accommodating. I know I don't make your life easy, and that of attendees because we're supposed to be the monthly webcast on the first Tuesday of the month, and we've tried probably all days in the week already, right?
Yeah. we
So
we kept I think we kept it relatively consistent,
yeah.
but there's a one or two outliers where we just couldn't manage. This is one of those weeks. Obviously first Tuesday of a month, the third was a public holiday in Germany, was me being on the road in London, you not being there as well.
Yeah.
So we couldn't really make it. So we try
Well,
to
yeah, I'm sure people understand. I mean, the great thing is that we've kept delivering month after month, and
yeah,
that's the important thing to me. And I'm really happy that we're on 21st already. So
me
yeah,
too. And speaking of that, I think if you haven't looked at the recap blog that we published, then please have a look at that. It's out on our the Neo4j developer blog. Let me here, I should have the link here. Let me put that in. Why is this so weird? Sometimes Medium makes completely ridiculous links. Here it is. This is much better.
yeah, we I think that was a great one in the end. So we had a substantial amount of content and material over the months and over the years, and it kind of made sense to kind of put a bit of structure, and you've done a great job at putting it in written, because that I'm sure that will help people find their way in the super rich catalog of content that we've created.
Exactly, and we had defined by admittedly by coincidence, they came to be basically these four themes out of the the background of content we had during these 20 episodes of Going Meta, and a couple of them identified sort of themselves, which made sense to include them and to split it out a little bit. So if any topic is not quite interesting to you, but generally the topic of semantics, ontologies, taxonomies, knowledge graphs, all of that, if that is something you're generally interested in, but you think, okay, the episode right now maybe not so much, or a different one, then go back to that blog post and see that there is a couple of themes that were identified, a couple of episodes, and you can find the one that probably makes most sense for you then, or which you think is more interesting. Um, could be more interesting for your case.
Good, and I'm sure you want to talk for at least a minute about something that's coming up,
Oh
right?
yes, yeah. It's nodes, obviously. Happening in on the yesterday, I think, to the day, or if it depends on what time zone you're in, but on the 26th, so in 3 weeks, more or less, is when nodes is happening this year. Let me put a link in chat as well. So it's really going to be a fun and interesting event, and very exciting on all kinds of fronts. So if you haven't registered yet, go to the link I posted here, or go to neo4j.com/nodes, and you find everything there. The agenda is now live since a couple of days, so you can check that out. If the trendy hot topic of vector, Gen AI, and everything, chatbot, chat GPT, all that stuff, open AI, you name it, if that is interesting to you, there's like I think I wrote an email with a couple of highlights, 5 or 6 sessions on LLMs, open AI, Gen AI, vector, last week. Um, but I had to skip, like, I think probably another easily 5 to 10. So if that's your game, then definitely notes will be interesting to you. If you think, oh my god, let me leave me alone with all of that, we have other things as well. So we talk about all kinds of things. On visualization is a big part. Everything app development, smarter, better app development with graphs is a big one. So um, I think you'll find something interesting there, and it's happening across all the time zones. So depending, or independent rather, independent on where you're based, you have sessions live in your time zone, and then the rest you can obviously watch on demand. So that's the beauty of it all. So that's going to be available afterwards on our YouTube channel.
That's great. Yeah, everyone join notes, and because it's gonna be great for sure.
Yeah.
So yeah, so I guess we're on to today's topic, which
Today's
is
topic, yeah, fitting to what I said earlier.
exactly no surprise, semantics in the title.
Yeah.
Um, yeah, and as usual, I'm going to try and share my screen, put the video to the side, and do a short introduction as we always do. Let me know, Alex, when you can see my screen. I should be sharing my whole desktop, but I'll go into slideshow mode. So that is, just the previous title. And like I say, when I say that I don't make Alex's life easy, I was saying, hey, what about these? The difference between, well, what? It's like so we ended up agreeing. Yeah, and that's exactly the reason why we went with this topic today, right? So we hear loads of talk about semantic search, and I think there's two very distinguishable and very clear types of semantic search, and that's how we agreed. Alex suggested a much more reasonable title that was much clearer. And the two approaches are the one based on vectors, based on embeddings, and the one based on graphs and path exploration, which is something that we've talked about in previous episodes. But that's the subject of today, and of course, in the backdrop, of course, is the fact that a few weeks ago, couple of months now, right? We released the vector index and enable vector search capabilities in Neo4j, and now we can combine the two and explore the two together, and that's exactly what we're going to do today. So that's the history and the rationale for today's session. And well, like I mentioned, I'll spend 3 minutes giving the context, and we'll go ahead and get our hands dirty with Neo4j on a sandbox. So where do we start? If we want to understand semantic search, we need to understand semantic similarity first. And if we want to understand semantic similarity, the two types of semantic similarity that exist, we need to understand how data is represented in general in AI, right? And in AI, these kind of two big spaces, right? The one that's called the area that's called knowledge representation, that uses what's called a symbolic representation of information, the one you see to the left, where graphs fit. And then there's the more machine learning focused, where information tends to be represented in the form of vectors, right? So knowledge like the one you see in that sentence, like apples and oranges are both fruits, can be captured in many different ways. So you have seen how we have represented that in a taxonomy, in an ontology, in a graph, basically. So you say that an apple is a type of fruit and an orange is also a type of fruit. And in the context there, you see that there's a relatively short distance between these two concepts. So there's some kind of proximity between them, some similarity, and that's what we mean by graph-based. That's of course the biggest simplification, but essentially the graph provides the context that explains the semantic similarity between two concepts like apple and orange. And again, semantic is a general term to refer to the fact that we don't do string similarity. So you can think of, dog is close syntactically or from a string point of view to dock as DOCK, but the meanings are completely unrelated. Right? So these would be one type of similarity, and there's search that enables these type of inaccuracies, which is fine, right? When you want to find words that are not explicitly or not explicitly, but not exactly spelled in a particular way. But we're moving from that type of search and that type of similarity to one that's more based on the meaning, and the meaning can be captured in a graph, and the graph provides the context. So that's one type of search. That's one type of similarity. One type of one approach to AI, which is knowledge representation. Then on the other side, we're not as explicit. I mean, the bit to the left, someone has to go and say, I know that an apple and an orange are both subcategories or types of fruits. On the right hand side, what we have is the result of probably exploring and learning over a large amount of examples. So the sentence that you have there might be a fragment of a chapter in a book or an article or a blog post. And that's the approach that we follow in the machine learning space. So we learn from loads of examples, and we find that consistently apple tends to appear in text close to orange and close to fruit. So we're capturing that in some way. It's much less explicit. So what you see to the right is the way we tend to capture this knowledge, and it's in the form of a numeric sequence, right? Well, a sequence is a vector, right? So we represent, and we won't go into how these embeddings are calculated, but there's a numeric representation of an apple, an orange, and a fruit. And this numeric representation has very particular characteristics, and is that it reflects the fact that there is a short distance between apple and orange. And that's completely independent on how you type it. Because if you do, let's say, if you had the embedding for let's say a plum or a pear, I mean, it will probably close, because these are topics that tend to appear close together or related to each other in the corpus, in the data that's used for training. So both, as you can see, capture some meaning, some semantics, but in very, very different ways. Let me take a pause here. Am I making sense, Alex? Is that clear enough?
It's clear. It's always a little bit difficult, I think, if you're not into the topic of the topic of vectors. I think it's a very pointed topic. No pun intended here. But it is. If you look at it like this, it can be very complicated and can be very confusing, because you see, okay, I see 0.2435 comma 3.7 and so on,
Mm-hmm.
and I don't know what that means, because obviously I'm a human and not a machine, and I cannot read that in that way. I think when I was when it first explained to me, somebody said, okay, think about the RGB color spectrum. You have a three-dimensional space, and you think you want to point out a point in that three-dimensional space, and that point is a color. And if you have 115, 50, and 64, that is a specific color, and that color is in that three-dimensional space somewhere, and then you can look at that, and that makes it a little bit more understandable, and that makes it a little bit more clearer, also with depicting it as arrows through a space
Mm-hmm.
in a field, that helps a lot. But it is a complicated thing to understand. But once you think, okay, you don't necessarily, you have to don't worry about as much maybe about the individual values, but more about, okay, what is it, what is this about, what is the point of this vector, then I think it makes more sense, and you understand it a little bit better.
Absolutely, and the whole point is that the representation to the right. We're not. I mean, it doesn't even make sense to try and make sense of it, because
Yeah.
what's the powerful thing is that this distance, and there are some functions to compute that distance, can reflect the fact that these are related concepts. And again, why there's obviously a very good reason to go with the one in the right, and you probably have figured that out. The one to the left is human curated. We have to go. I mean, it can be discovered from the data, but someone has to go and say, "Hey, an apple is a type of fruit," and that requires domain understanding in that simple example. But think of your enterprise, right? So it's human curated, it's controlled, and that's these are very important characteristics when we compare them. But the one to the right, it can be completely automated, so you can just give a huge amount of data, and it will learn these vectors for you. So automation is a huge factor there. because, well, if you think of the a session with ChatGPT, you can ask about anything in the world. You cannot even think of capturing everything in a graph,
Yeah.
right? So you will pick fragments of it, the ones that you care about, the ones that your enterprise cares about. But, of course, with huge amount of resources, you can fully automate the process of learning these type of representations, and they're very powerful. And the great thing is that we can have the two and combine them together. But I think it's important to understand the two, and that's what the example that we're going to be using today.
Yeah.
Good. So, well, this is the starting point, right? So we have two different ways of representing, capturing knowledge, and depending on which one we use, that will open different possibilities for comparing similarity and applying search. So this is material that we've shared in the past. For the first approach, we will start with, let's say, some unstructured documents. Again, we're going to use a collection of articles that we've used in the past. There's a process that will extract entities out of it and make them explicit. And then we'll enrich that with an ontology, with a taxonomy, with a classification, something that provides additional context, something that puts in context the apple with the orange, or a topic with another because they have a common ancestor, or because they can be classified in an ontology. Because when we have this in a graph, then we can find the similarity between two, semantic similarity between two documents, based on the fact that there is a path that connects the two across the graph. Advantages of this: I mean, it takes longer to build, it requires expertise, but it gives you control over the responses that you get. So you can explain that this is similar to that because there is this path across the graph. And we touched on a bunch of standard similarity metrics. There's a whole episode on this. I can't remember the number, but we'll add the reference in later on. So this can be done, and it's a very powerful way of computing semantic similarity. Now, in the vector space, what happens is, every element in the world is represented as a vector, and we can do pick two and tell what's the distance between them, what's the semantics. But these are implicit relationships. We have less control over. I kind of understand that a cat is close to a dog, but it's not that I can really explain it. I cannot uh, provide the rationing, the rationale, the reasoning that the model is implemented, because it's just capturing this numeric representation, and in the end it's purely a distance function. So it's like a mathematical distance, as you can think in a 2D or 3D space, except that it's a much more highly dimensional space. So that's the idea. These are the two approaches, and I'm going to try and show these in an example. And like I said, the first part, we're all familiar with it. If J is a graph database, we can capture the relationship, build the taxonomies, build the context around elements in the graph. What's relatively new is the vector index, and this is just a screen capture of the announcement. You have the links down there. So there's a blog post with the announcement, but probably more interestingly, for the attendees here is the link to the manual as well, where you can see how to create a vector index, how to populate it, and how to create it. It's pretty straightforward. I mean, we will add properties to the nodes that are vectors, that are long vectors, numeric vectors, and we will index them using the vector index. Once we have it there, we can do pretty performance searches based on that. So that's exactly what we're going to be doing. So with that, let me stop with the presentation. And as always, I've already started my sandbox here, fresh one. It's already created, and I've been extremely diligent this time. And as you can see, there's already all the content there on the GitHub repo.
Ooh. Yeah.
So you will see that we have all the elements. So I'll probably go a bit quicker on the construction of the graph and population of the indexes and all that, and then focus more on comparing the two types of semantics, similarity and semantic search. So yeah,
It's good. And if you watch this and have any questions, then
please.
please use the chat while you can. and I'll have an eye or two at it, and we'll read out your questions.
Absolutely. So yeah, so the cipher, if you want to code along, but then more importantly, all the resources are here. So we're going to be using ontologies that are already in this folder, and the data folder contains the data and even the embeddings that have been created. But let me take you step by step. So like I said, we have a completely empty database. And the first thing we're going to do is import a collection of articles, unstructured data, right? And you will find that in the data directory. So if you go there, that's a collection of technical articles in the form of a CSV file. So you'll have the URI, the body, the title, and a few extra fields. So that's pretty straightforward. I won't spend too much time on it. A very quick load CSV that will just create a single node. So that's what it looks like. So load CSV of the file, and it creates articles and populates the title, the body, and the timestamp of the articles. So we have a bunch of them, small set. And we can see that if we click on any of them, we have all the details here, right? The time, the title, the URI, and the body, which is the full text of the article, if they happen to be referenceable. So if you click on it, you will get to the article itself, which is pretty handy. But yeah, so we have our article. So the first layer is there. And now what we're going to do is add some context. And again, I'm going to run this quick, but we have used in the past something like Wikidata for that. In Wikidata, these are technical articles that talk about programming languages, that talk about databases, that talks about systems. So I thought, well, in Wikidata is a super rich knowledge graph with a definition of loads and loads of categories that form a great taxonomy, and I'm going to use that. And again, this is in the in your resources folder. If you go to the ontology directory, you will see that there's a dbpedia extract, and you have the query on how to produce it. So if you're curious, you can grab the Sparkle, run it on the Wikidata Wikidata Sparkle endpoint, and that produces an export that I've represented in SCOS. SCOS is a language to create knowledge organizations, taxonomies basically, and that's sufficient for me. As you know, we can import SCOS is one of the RDF-based languages, and this type of thing we handle with Semantics. So the next thing that I'm going to do is, as usual, create the constraint so that Semantics doesn't complain for a change. Alex, instead of the error thrown, I created up front. So there you go. So we have an index for the URIs, so that it takes care of the linkage based on the URIs. The next thing is I will go with all the defaults in the configuration. Again, very briefly, in Semantics, you can make a number of choices in terms of how you want your RDF imported. In this case, I'll go with the basics, and I'll say that I don't care too much about preserving the vocabularies, but I will go ahead and import. I will import the ontology with a single line instruction as cause, because that's the vocabulary that we're using. Import, fetch. We pass the URL of the file that I just showed. Remember that it's the raw version, not this one, because these are the human readable and it's HTML. You have to go with the raw one. So if you pass that to Neo4j and you indicate that it's turtle serialization, in a few seconds, you should get it imported into your graph. So now we have the taxonomy formed by 11,000 roughly entities linked to each other, and we can see what that looks like, because there you go. So that's a small fragment, but let's zoom here. So we have make it a bit bigger. It's using the Wikidata IDs, which are not very user-friendly. So let's go with the preferred label, which is probably much nicer. There you go. So, and we can make it a bit bigger to make it readable. So you see there's the notion of a programming language, and that has multiple subcategories, subclasses. So again, this is the kind of thing that you can tweak in the configuration. By default, Semantics will create a subclass of relationship that we call SCO, to make it compact. But if you're more comfortable with other name, you can configure that too. And the elements in the taxonomy are labeled as classes. So there you go. So and you can keep expanding, and these will form a large network. Ideally, it should be close to a tree, but not necessarily. But it's a rich classification of the systems, databases, programming languages space. So we have the two parts. We have the articles. We have the taxonomy, the classification. There's a little step of data cleaning that we have to do, which is if you think of a tree, a classification, right, a taxonomy. You don't expect there to find things like shortcuts, like for example, you have
Squirrels would like this.
yeah. But the reason, I mean, as you know, Wikidata is a collaborative repository, collaborative knowledge graph. So it's not always perfect, right? It's an evolution, and sometimes you find, I mean, it's not bad. I mean, it's just redundant information, right? So you have the fact that I don't know. Since we're going with oranges and apples, I mean, if you have a blood orange, these red oranges is a subcategory of orange, which is a subcategory of fruit. If that normally forms a sequence of subclass of relationships. But if I could redundantly say that this blood orange, the red orange, is also a subcategory of fruit, which is something that I can't undo because this subclass of is transitive. So that's exactly what I'm doing with this. I'm saying, well, if you find a shortcut of this type, I don't really need it. I mean, it doesn't hurt, and I could keep it there. But I'm, a bit of a perfectionist here, and I like to have my tree clean. It's not necessarily a tree, but I don't need these redundant relationships, and I remove a few thousand of them.
Yep.
Still keeping I remove 500 of them, right? So there you go. So now we have the two components. We have the context, the graph, and we have the articles. Now what we need to do is extract the entities that are mentioned in this natural language text and make them explicit so that they connect with my graph and they form this contextualized representation that we were talking about before. Now, because it would have been a super long episode, I'm going to save you from having to do that. And I've already, but we, remember, Alex, we did that in episode 2, I believe. So if you want all the details, you can go there and have a look at that. What we're going to do today is go to the data directory, and you will see that there's extracted entities file. So what I've done is I've done it for you already. So for each of the articles, we've run the process of effectively what we use, if you remember, is using the natural language processing wrappers that are in Neo4j.
Yep.
So, and by these, you can use your preferred, I mean, these are wrappers for the three main cloud, natural language services of the three main cloud providers. I believe we use the Google Cloud one. So basically with simple instructions in Cypher, in APOC, you can take that string, invoke this natural language processing entity extraction procedure from Google, and it will return a collection of entities that we will then represent as nodes. So in order to save us the time of having to do that, I'm giving you already the list of entities that were extracted. And it's very interesting that the Google service in particular brings them back annotated with the Wikidata, Wikipedia URIs, which is great, again, to simplify the process of linking. Because as you know, because I've mentioned it several times, the linkage, I mean, the entity extraction is one thing, but the entity linking is not an easy one, right? Sometimes you have to apply heuristics, sometimes you have to approximate. But in this case, because we have them annotated with the URIs, then they just stitch like glue, and that's perfect. So here's what I'm doing. I'm taking this file where I have my extracted entities. Basically, what I have, as you have seen, is for this article, identify with the URI. These are in this case, there's two entities. It's about Rethink DB and about NoSQL databases. For the second one, we have another two pair of entities. So what I'm doing is scanning this CSV file and making those nodes. So I will have to match the article on the URI. I will match the class that will exist, hopefully already. If it doesn't, we'll lose that. But in this case, well, I'm just picking the ones that link nicely to the ontology that I have. And if I find the match, then I'll link them with that refers to. And again, that's my choice of naming, but you're free to call it the way you prefer. So This should be a relatively quick one. And what we have now, as you can see, is our old articles, now hopefully enriched with, let me make this a bit bigger. How do we do that? Here. We can zoom it in, and we have the node representing the article, which is the blue one. We have a number of entities that have been extracted through this process. So this article, I don't know if it's readable, but it's about Python, Zookeeper, SQL, Java, and some others. And these are already connected to our taxonomy. There you go. So that's how we've kind of closed the gap between the two. Make sense? So that's the,
Yeah,
kind of
cool.
a super fast step-by-step description of how this works, but you can look at more into the details of the actual entity extraction. So okay, we have all the elements we need now to start using these for to calculate semantic similarity, at least graph-based. But we have the other part, and the other part is the vector-based. So well, what we're going to do is now we have our articles nicely connected to entities and classified in a taxonomy or contextualized in a graph. But at the same time, I'm curious to see what happens if I take the body of the article that I use for entity extract and make explicit here. I'm going to take that and I'm going to embed it. I'm going to vectorize it. And again, here, I'll simplify. I think I'll share the code because it's a pretty straightforward. In this case, I've used the OpenAI API where you pass a text and it returns an embedding, right? So I have it in a Python notebook. Again, I've done this in advance, and there you go. So the kind of thing that you get is for each article, you get an embedding. So I've done that so that we don't have to run it live and save some time. And now, just like the other data elements, we have it here. So we have the article embeddings, and this is in JSON format. No particular reason. I just felt like creating JSON this time, and similar structure. So for each of the articles, I have the article URI, and I have the vector resulting of embedding the body of the article, the text. So what I'm going to do is parse this file and enrich my my graph with a new property that will represent the body of the article, but in the form of a vector. Make sense?
Yeah, very cool.
But because I want it indexed, I'm going to first create my index. And that's a very simple instruction that you will find it all in the link that I shared before to the documentation. We're creating a vector index. I'm giving
Also
it a name.
added it to the description.
Oh, fantastic. Thanks for that. So I'll give it a name. That's going to be my article embeddings index. And it's based on nodes of type article. So I'm going to build it out of nodes of type article and a property that will be called embedding. It doesn't exist yet, but I'm going to populate it as I said. So this is the similarity that I'm using, cosine in this case, and the size of the vector. So pretty straightforward, just like any other index. It's already built in. And the next thing is, okay, let's enrich the this article description with the vector representation that I'm going to get from my JSON file that I just showed. So again, remember that there was a pair article ID vector. So all I have to do, actually, let me show you what that looks like, because it was a JSON file, and if you are familiar with the APOC load JSON, it's just another one of these super useful functions in APOC that will let you point at a source of JSON and just parse it, right? So if I return, in this case, it's just a list. So if I return value.id, I think was the first element. So there was value.id and value.vector. These are the two value.vector. And just show the first one. I don't need to show more. That should give us an idea of what we have. There you go. So we have, it's been truncated, but we have the URI of the article and the vector. So that's exactly what I'm going to store, right? So instead of printing it out, what I'm going to do is I'm going to look up the article by ID, right? I'll find the article, and then I'll add a new property called embedding, where I will put the vector. And these will automatically be indexed in our vector index because I've already created that and indicated that that's the property that's meant to be indexed. So if I do that, again, it's a pretty quick process. In this case, again, you will have to generate the embeddings. You could do it all in one go. And here you have to pick your preferred. I mean, I've used OpenAI, but you can use use Vertex, you can use your preferred model, and you could perfectly do it on the fly, right? As you write to the graph or in batches, you can scan the nodes, the articles in the Neo4j graph, take the text of the property, call the embedding function, and store directly. I've done it, in these intermediate steps so that you can use it, and it's already done there for you. But I'll share the code on how to do that with OpenAI because that might be useful for
Yep.
people there.
Yep.
Perfect. So now we have it all, right? So we have the articles contextualized with our graph and also embedded and indexed in our vector index. So what are we going to do? Well, we're going to start computing similarity. Let's get started. So I'm going to take two articles, and I looked them up by title. I can look them up by a URI, but I thought it would be more readable like this. So I'm looking for an article that's called Performance Testing Neo4j Database using Bolt and JMeter. And I'm taking another one, which is Couch-based GeoSearch with ASP.NET Core. So these are two articles that have a property. Each one of them have a property called embedding, right? Mm-hmm. So we can use the function in GDS that's cosine similarity. That takes two vectors and returns literally the distance between them, right? The similarity between us. Distance and similarity invariance from each other. But it says it's as simple as this. So this will tell me, okay, the distance between these two, between these two is 0.74. And that has a meaning. I mean, that has a meaning in context, right? If you put it, compared to others, you will be able to tell this is more or less similar than another one. But that's what you get. And that's what we were saying before. It's great. It's super powerful, but it will not give us the explanation of why these two articles are similar or how they are similar. So we have to trust the accuracy of the model that we have used to embed. And again, I've used here a general purpose model like OpenAI. I can't remember which one of the models was it. But you could perfectly use a model that's trained on this type of data and maybe get more accurate embedding. So this is, I'm not saying that this is the perfect solution, but I want people to get a clear understanding of how that works. So we have a way now of given two articles, take the vectors and say that's how similar they are. And that's super powerful because ultimately what we want to do is say, because you're reading this, you might want to read this other one, or I'm interested in things that are similar to these. So that's vector search, and as you can see, what I'm doing is just using the not search in this case. It's just vector similarity. We'll get to search in a minute. What would it be like in the graph-based approach? So can do a number of things. So as you can remember here, we want to follow explicit paths and understand how these things are connected. So I take the same two articles, and now I say, well, articles are connected to my classification through the refers to relationship. So from my article, I can get to some concepts, some semantic descriptions that are connected, hopefully, through my context, my taxonomy, my ontology. So I could explore that graph. So here, these are just possibilities. And what I'm doing is using the path similarity implementation that we also talked about in one of the previous episodes, right? The one that I've mentioned here. Path similarity is one of the simplest ones.
16.
Excellent, thank you. You got my back there. So essentially, it will find how long the path connecting the two elements in a taxonomy is, and based on that, determine roughly how similar or how distant they are. So that's what this function does. So we pass the two concepts, and well, if you can remember, there was an option, a configuration option, when we cannot assume that the taxonomy, the context is a perfect tree and all the elements have a common ancestor, like a thing, like a root element. Maybe that is the case, maybe that is not. So the implementation, the definition of this algorithm, this similarity metric, says that when you can by default assume that for the root elements of the multiple taxonomies that you may find, you can assume that there's a simulated common root. But in this case, I don't want that to be the case. If there's not an explicit path, don't make up these simulated routes. So this is a configuration option, and what I'm doing if I run this is I'm going to get well, first the similarity metric, but then more interestingly is the explanation. And you probably saw in the second part that my path similarity not only gives me the metric based on the formula that you have seen here, which is this calculation, but I can also compute the path and return it, because that is the explanation that I'm after. So I know that these are similar 0.2, and again, you have to put it in context. It's I can't remember this one if it was 0 to 1, but again, the idea is that these two articles are similar because they happen to, one of them refer to Neo4j, the other one to Couchbase. That if you follow in the taxonomy, Neo4j is a graph database, which is a database management system, and on the other side, Couchbase is a document-oriented database, which is a data management system. So there you go. You have a path, a common ancestor there, which explains why these two are similar. And that's the curated aspect. So we are not relying on whatever data has been used to train the large language model that we have used to embed our data. We know exactly the rationale, the reasoning behind the similarity between these two concepts, between these two articles. We have a more visual representation of it. So you probably remember from chapter 16 that there's a variant of that method, path similarity path, that returns not only the value, the metric, but it returns the actual path connecting the elements. And that's probably a much more visual way of understanding it. And you see that Couchbase, this article, which probably should make a little bit bigger so that we capture a little bit more of the title. This article refers to Couchbase server, which is, like we saw, a document, follow the arrows. There you go. So that's the similarity path. And that's the explainability angle, which is extremely important. And that's something that we normally miss from the vector-based, more sub-symbolic, as we call it, where we don't make explicit the knowledge, but rather learn it in the form of a vector. So I'll take a pause here. Making sense so far?
Yeah. Sorry. Yeah, it makes a lot of sense. It's I think it's a great way of explaining these two approaches towards similarities, or towards finding similarities in um, in, uh, in your data. In no matter what you have, you can use either of those two systems to find it out and to discover if there are similarities. But if you're happy with not quite knowing what came about,
Oh,
then
exactly, because I'm sure you've heard about the problem of hallucinations and these
yeah,
kinds. The generative AI models typically, I mean, by definition, they're generative, right? So sometimes you want them to be creative, right? And that's great. But sometimes you want them to be accurate and not only accurate but explainable. Or you want to have control over the information that's used to provide an answer. And that's why approaches like retrieval augmented generation are being so popular, right? When you pass the question to your LLM, but at the same time you pass the context required to answer that question. But without going into this, we might cover that in future episodes. Here, I really wanted people, because it's important to understand what we mean. And when we say semantic search, yes, semantic search is any type of search or similarity that goes beyond the purely syntactic or string-based one. So here we're talking about meaning. And I can tell you that this article, whether it mentions Couchbase or not, I don't really care. I know that these two are related because there is a common topic. They talk about database management systems, even though that's not explicitly mentioned. So not semantic, but textual similarity would never pick that up. So that's semantic search. But one is very different from the other. And again, I'm not saying that one is better than the other. The answer is probably better together. But this is the foundation and I think the explanation of it. And and I guess that I'm conscious of time, and I don't know if there's going to be questions, but the next step would be, here we've taken two articles and say, well, what's the similarity, how similar or how different they are. But normally what we do is effectively do the search, and that's where the vector index comes into play. So what I have normally is, okay, I have let's say just one of the articles, and in this case I'm looking it up by URI, but I
Hmm.
could do exactly the same as before. This is the one about testing of J with JMeter, blah blah blah. So what I'm doing here is, okay, I have one article, and I have the content embedded, and I want to find which are the other articles in its proximity. And this is semantic search. I'm not giving you two articles and tell me how close they are. I'm telling you based on the index, and that's where the new feature is super powerful. Tell me which are the closest one, and that's what I'm doing here. I'm calling my vector index, and I'm saying, well, use the article embeddings, which is the one that we just created, and give me the top 5 based on the embedding of this article. So don't follow the path like we're doing before. Just take the embedding and give me the 5 closest one. Excluding, of course, the article itself. I don't want it to be returned, because if I did, I'm going to get one that's identical to itself, and that's not very useful. But this gives me a list of all the similar articles based, like as you can see, the article itself is a perfect match, which is not very useful. So if I remove it, I get the top 4, and I get a metric. And yes, it does make sense. Of course, this is an article about Neo4j. At least the first 2 that talks about Neo4j. That even the text search would have picked that up. Now the
Yeah.
question is, what happens with this one, and why do we think that's accurate? And that probably is, but we kind of have to trust the model that has generated this embedding. And the question is, can I trust it? And for future episodes, I mean, which are my options? Can I train my own model? Of course you can, but it's expensive. It's a huge effort. Should I fine tune it? Should I retrieve augmented generate? There's many options, but here let's understand what this semantic search returns, and that's what we're getting. And if I did the equivalent based on the other approach, let me show that to you, because here I would get something similar. In this case, what we're doing, and notice that here I'm not doing proper search, and I get back to that in a minute, but I'm doing the comparison, and I'm getting a similarity metric, but I'm getting also, and I'm not listing it here, but I could get for each one of them the path that explains why these 2 articles happen to be related. And that's the explainability, the control. And just to complete the explanation, and you will see how that impacts the results and how I have control over the results. These are the answers based on the taxonomy that I've imported from Wikidata. But let's say, hey, I'm an expert in my domain, so I know that there's the notion of software stacks, right? I know that there's the grand stack that combines, Node.js, Neo4j, GraphQL. There's the LAMP stack that combines, the mean stack that combines Express.js, MongoDB. So let's say I have additional knowledge, right? I know more things about my domain, and I want to use that. I want my semantic similarity to take that into account. So I take these ontology, or this additional knowledge representation, and I'm going to add it to my model. I mean, nothing stops me from keeping adding additional elements of information. Remember that this is all curated. I can bring them in and out as needed. So in this case, I'm doing an import request, pretty much like what we did with the Neo Semantics before. But in this case, it's not a SCOS representation. It's I think it uses OWL, right? There you go. So it's OWL classes. It uses still the labels from SCOS, but it's a different type of representation. Doesn't matter. All I have to pass is the reference and the serialization format, and this will bring additional elements. I mean, I could have I've been too quick to import, but I could have previewed it first. If I want to do a preview of what this brings, that's exactly what I was showing before. Let me make that a bit bigger. And we have things like there's the notion of a software stack, and we have 3 of them. I mean, there's like 3 mini taxonomies that describe the LAMP stack, the grand stack, and the mean stack. So it is another way of providing additional context for my search. So maybe if you're reading about PHP, you want to also read about Perl, because there happens to be a technology stack that combines the 2. And because I know that now, I'm offering you a new path for exploration. I'm providing you additional context, and I control that. That's the powerful thing. I decide what information is used to return that answer. And if I remove that, that's been persisted in the graph, and I rerun exactly this query, I'm going to run it again. Now I should get new results, hopefully. And there you go. So now you see that suddenly it's jumped to the third position, the one on GraphQL that was not there before. Why? Well, because now my search, my path exploration is finding that there's a stronger connection between these two, because now they have GraphQL in common, which is part of the grand stack. See how that goes, right? So this gives you the control and the power and the curation of the knowledge that's used for the semantic similarity, whereas the other one relies on the model and the data that has been used to train the model. But again, important, the really a powerful approach comes from combining the two, and the first step is to understand them properly. So that was the objective of today's session. So I'm going to take a pause. I've talked a lot, but I hope it was useful, and that triggers some questions. Hopefully, that was the
Yeah, it is. It is.
topic.
One thing I want to add, and maybe it's also, I think probably I'll end it end in a question. But when you said it's better together, so I think it makes sense if you stay with the picture of the fruit that came to me earlier. Is okay. Let's think about tomato. Tomato is botanically a fruit, but obviously you don't want to put it in a fruit salad because it's not really right. So if you have it in a classical ontology, it probably would land up under fruit because it's botanically categorized as a fruit.
Mhm.
Um, but if you look for something for, let's say, a fruit salad, if you go hardcore into the semantic search pattern through, it might come up as a suggestion, maybe not top ranked, but
Mhm.
potentially down there. But in a in a vector search, potentially you would grab it still for, not for your fruit salad, but for a vegetable kind of based thing, because it would still pick it up as it is
Yeah,
locationally closer to a cucumber, which is obviously not a fruit.
yeah,
So if that makes any
yeah,
sense, yeah,
absolutely, yeah, and yeah, and that things are becoming a bit more subtle, because they're semantically related. So
yeah,
a tomato is close to an apple, yeah. But if your question is more, and we didn't get into how to answer natural language questions, because another thing that we could do, and that we can do with large language models, is, hey, I'm making a salad, what should I do? And in that context, maybe the training data provides additional information on whether you should put that or not in a salad. But so the fact that they are semantically close, that's a fact. And then on the symbolic approach and the knowledge representation approach, the graph approach, I've shown the most basic construct in an ontology, which is a classification, a taxonomy. But there's many more. I mean, you can express disjointness. I mean, you can overlay multiple ontologies. So you can say, yes, there are two instances of the same category because they're both fruits. But in the same way I've added the technology stack, I could say, hey, in the context of a salad, these two things should be disjoint, or maybe this is incompatible with that. So you can keep enriching that. And again, these implementations of semantic similarity, graph-based semantic similarity, are probably the most rudimentary and ones that can be the starting point. But the the important thing is that you have the control, so you can traverse the graph in whichever way you want. So you can say, find a connection across my graph, but block going through nodes of a particular type. So really, the powerful thing is you can use standard metrics, but you can also totally own that process and determine how and you want similarity to be computed, because whatever you come up with, you will be able to explain it, and you can say this was discarded because it went through a node of type salad, and salad is a blocker for this type, for an orange, for example.
yeah,
I've seen an orange in a salad sometimes.
yeah,
Anyway,
yeah, yeah.
but yeah,
There's always,
what I mean. So
yeah,
you can keep adding context, and what I've shown is really the most basic type of representation, which is a classification.
yeah. Cool. Thank you very much, Jesus. There were a couple of questions, so let's take them
Sure.
on. Peter asks, would you normally have multiple paths between articles?
Absolutely, absolutely, and I kind of quickly went over that, but yes, I mean absolutely, because remember that an article connected to a number of entities, a number of things. So an article was about Neo4j, about Java, and then for each of these concepts, you will have a path. So you will have a number of them. Again, another option for you to determine how you want to combine them. You want to add the more paths. Probably the more paths means the stronger the similarity. Maybe you want to average them, maybe take into account. So yes, absolutely, there will be, and as you keep adding, because that's what we did when we included the technology stack. So you're offering new paths for exploration. So the more knowledge, the more curated the knowledge about the domain, the more control and the more additional paths you can offer for exploration, and the more the richer the semantic similarity will be. So big yes to that. Absolutely, there will be multiple paths between articles.
A comment from Mark: using the context to explain to skeptical managers is critical. I think that's very true. Yeah, if you have your black box has something, and somebody asks you, "But how did you come up with that 20% similarities?" Like, yeah, well, my machine said something and printed it out in the end. So,
Yeah, and maybe this case sounded like not non-critical one, because worst case you recommend an article that's not relevant, and no one will click on the link. But think of a more important decision, right? Think of an investment, think of a medical decision based on other examples. You really want, in some cases, explainability is a must.
yeah.
So totally agree.
And one more question from Ryan. I want to figure out a way to do this for property records, including spatial similarity, where then Dave suggested maybe K nearest neighbor, if that could be something to use.
Well, actually it's approximate nearest neighbors. I mean, it's kind of a different implementation, and I mean, on that I will have to do a bit more research, but maybe the documentation you'll find. But it's based on nearest neighbors, the search on the vector index. But the question was whether it can be combined with spatial similarity. Exactly. I mean, the spatial is yet another index. So again,
yeah,
the more information you make explicit in the graph, the more elements you have to maybe your similarity in the end could be a combination of these contextual connections between entities, but you can bring into that the geographical the geospatial proximity as well. So absolutely, so this is yet another element to bring into the semantic similarity comparison.
yeah, absolutely. And one more from Dave: vector index is the community edition, or where do you get to able to play with vector index, vector search? I think it's currently a beta feature, so it's available in all the editions. Obviously, Jesus, you just showed it on Sandbox. If you download, you need to download the latest version. Well, not
Yeah.
not 5.12, but at least you need to.
It was 11 when it was
5.11
released.
exactly.
Yeah.
Anything after 5.11 will have it as a beta functionality, and then you can explore.
Yeah. Absolutely. So that's like I say, I use Sandbox, and you have it there. So approximate nearest neighbors. Yeah. Thanks, Mark. That's what implemented, and so yeah.
Yep. Cool. I think that is a good way to end the episode. Thank you very much, Jesus, for presenting this, for going hands on again, and showing the code, especially with the vector search. Very interesting, and good to see it hands on how it works. Particularly because it's such an interesting topic, and so many people are wanting to know more. But I think there's a little bit of a gap between what can it do, how does it work, what can it do for me, how can I use it, and what do I want to use it for exactly. And I think that's I think we hopefully we clarified a little bit
and
on that
and
front.
and on that topic, as always, everything we've used is already in GitHub. So please go and play with it and let us know how your experience goes, and yeah, enjoy.
Yeah. Cool. With that, let's close it out. We'll be back in November. Date to be confirmed, but we'll look to be back in the regular schedule first Tuesday of the month. So that would technically be the 7th of November. Let's see. I might be traveling that week, so we need to find a way to see how we can get that to work. But I'm sure we find a way. Between now and then, obviously Nodes on the 26th of October. So please check it out, have a look, register for it. And next Tuesday on the 10th, the final Road to Nodes workshops is taking place. This one on geospatial data with Will Lyon. So if that is something you're interested in, check it out. Tuesday, 5 p.m. Central European time. Yeah, early afternoon in Europe, early morning in the States, and somewhat evening-ish in Asia. So if that works for you, register now, and hope to see you on the Tuesday. Yeah, and with that, thank you, Jesus. Thank you, everybody, for sticking around on a Friday afternoon, if it's your afternoon, or Friday morning for Mark, early morning indeed. And thank you, Jesus, again.
Thank you, Alex, and
Thank you.
see you all next time.
Next time, exactly. Take care. Bye.